Yeah, Venkatesh, you can start now. It's like the student also joined one more. Yeah,
Yeah,
you can
sure.
start. Neha will continue after 5 10 minutes, she told. So now you can
Okay.
start it. Okay.
Okay. So, good evening, everyone. Welcome to the demo class on analog circuit design. So, in this session, we will go over the overview of topics which are offered in this course. And my name is Venkatesh. I am a circuit design manager in Texas, and I have around 12 years of experience in analog circuit design. So if anyone has any questions, then you can interrupt me or you can ask questions at the end of the session. Okay, so let's start the demo session. So about Upgrade VLSI Technologies, it is one of the best institute for freshers and working professionals for VLSI studies with 100% of placement assistance. So at the end of the course, each students will be given chance to appear in interview. So we have around 200 plus companies. I mean connection with the 200 plus companies. So you will be given with opportunity in one of the companies or few companies, and industry standard tools are available, and each students can access industry standard tools through VPN, and those tools are available 24/7, and all the trainers are with minimum 12 years of experience to provide a quality hands-on experience, and the training material will be given both soft copy and hard copy to each students, and mock interview will be conducted at the end of the course, and there will be few personality development programs also will be conducted, and 100% placement assistance will be given to each student. And why to select Upgrade VLSI technologies? So these are the few reasons. The first one is expert trainers and curriculum. So our courses are designed and delivered by professionals in the industry and who is having around 12 years of experience and who is working on branded high MNC companies. And the second reason is 100% placement support. So the students who completes the course and who meets the criteria, they will be given with 100% assistance until they will get placed. As I said, we have a connection with 200 plus companies. Some are product companies and some are service, and few are startup companies. And the third reason could be online courses and affordable fees. The courses are online. The soft copies of uh, content will be given to each student, and the fee is affordable, and even the EMI facility is enabled. So you can contact HR and get the details of EMI, how it can be converted into EMI. And the fourth reason could be the powerful EDA tools. So we have industry standard EDA tools for hands-on training of our students. So during the training period, each students will be given with a VPN access. So by logging into VPN access, they could be able to access the EDA tool, and those tools are available 24/7. So these are the key informations. You will find content of the course in this link. So the duration of the course is 16 weeks. So the mode of the study is weekend online classes. On Saturday and Sunday, 3 hour, total 6 hour classes will be conducted, and it will have two set of classes. One is teaching class, another one is lab session class. So in a teaching class, the theories will be studied, whereas in lab class we take few examples, and using those examples we will try to understand the concepts which are studied in teaching class, and there will be a good number of assignments and problems will be given to each student. So the solution will also be tried in lab session. So tools and VPN cadence versus so tool is given to each student and it is accessible at any time. And course material, the soft copy will be sent to each student, and the hard copy, if it is needed, then it will be a courier to the respective addresses. And this is the contact info, so you can send an email at info@upgradevlsi.com, and this is the mobile number. So eligibility, who all can enroll for this course? The students who completed or pursuing a MTech or MS or ME in VLSI or embedded or any other specialization. So they are eligible for enrolling into this course. And the professionals who is having 1 year or 2 year experience, if they want to uh, uh, enhance their skills in analog circuit design, then they can opt for this course. Or any other professionals who is working in some other domain, it can be digital design or digital verification. If they want to change their domain to analog circuit design, then this is the best suited course for them. So industry salary after placement, as a fresher, one can expect 4 to 6 lakh salary, and with 3+ year experience, the salary will range between 12 to 15 lakhs. With 5+ experience, uh, 5+ year experience, the salary will vary between 25 to 30 lakhs. The job role will change from individual contributor to team leader. So in a team of 3 to 4 members, you will be like a project lead. And with 10 years of experience, you can expect around 50 to 70 lakhs of a salary, and the job role will change to managerial role, where a few people will be reporting to you directly. So this is the salary you can expect in as an analog circuit designer. Placement support, 100% placement assistance till each and every students will get placed. And we have a connection with the 200+ hiring companies. Few are product and few are service and few are startup companies. And a few MNC companies are listed here. L9T, Capgemini, HCL, Wipro, Cynat, AMD, Synopsys. So we are in connection with these companies. And as I said, the tools will be provided to each student. And at the end of the course, there will be mock interview just to make students comfortable to placement interviews. And there will be personality development courses, programs will also be conducted. And the minimum salary you can expect is 4 to 6 lakhs if you are a fresher. But if you have 1 or 2 years of experience, then definitely you can expect more than this number. So these are the few companies we are in connection. So you might get placed in one of these companies. So these are the few students who got into different job roles, who opted for courses in our upgrade VLSI technologies. So you can discuss with these people and get the feedback. And if you think the courses suits for you, then you can opt for the courses in upgrade VLSI. So these are the content of analog circuit design. So we will go through each module one by one. So so for each module, there are two set of uh, classes. In the first one is teaching class and second one is a lab session class. So in teaching class, we will look at the basic concepts. We will look at the equation, we will draw the transfer function, we will look at the Bode plot. The theory part of all the analysis, we will look at the teaching class. In the lab class, we take few examples. So using those examples, we will try to realize the concepts which are studied in teaching class. Okay. And in lab session, there will be some assignment will be given after each session. So after a week, we can look at the problems which are given. We'll try to solve those problems in lab session. So since we will be going through each module one by one, so I'm going to skip, move to next slide. So total there are 14 modules. So 13 module is on a project and 14 is on mock interview on personality improvement. Yeah. So total 74 theory teaching classes and 30 are lab classes. So module 1 focuses on the device physics. So here we will look at the structure of PMOS and NMOS MOSFET, and we will look at even the transistor level transistor characteristics, and ID and VDS characteristics of PMOS, and we will look at even the NMOS characteristic, and we will study different region of operation. So you know that MOSFET works in saturation region. So this is the saturation. So this is the linear region, and this is the cutoff where current is almost zero. And there is one more region will come here, that is subthreshold region. So we will look at all these three regions. We will write the expression for all three regions, and we will study the condition which determines in which region the MOSFET is operating. Okay. And next we will look at the small signal modeling of both PMOS and NMOS, and we will try to measure the GM depending on the voltages in lab session, and we will look at the R naught, and basically we will try to relate all this GM and R naught with the gain of a MOSFET, and we will look at the output impedance, how it is varying. So those kind of studies we will do in this module. And the MOSFET can be used as a resistor in linear region, or in some current mirror technique, using that in amplifiers to increase the output resistance. It can be configured in saturation region. Okay, so that's how we increase the output resistance. So the MOSFET can be used as a resistor depending on the requirement. So it can be used as a switch, or it can be used as a capacitance. So we will look at how the MOSFET can be configured as all three these components. Okay, so we already know that MOSFET can be used as an amplifier. So along with that, we will look at how it can be configured as a resistor, switch, or capacitor. And also we will look at the second order effects of MOSFET. Like if we go to lower technologies, then the smaller length of MOSFET will cause some secondary effects. So that is called short channel effects. So we will look at short channel effects in this module. So module tool is for a cadence tool introduction. So here initially we will introduce the Linux operating system. So in this you will be given with a few set of commands. This is a very simple few commands like copy recursively, or move, or rename the file from source to destination. So along with that, the few set of commands will be given to you just to make yourself comfortable with Linux, because that all the tools will be in Linux. So those commands which are really needed for you, those will be given to you. Okay, so once you know the Linux operating system, the basic commands, then the cadence virtuoso tool will be given to you, and you will be able to access through VPN network. Here we will introduce the basic file system in cadence, like a library, cells, and different views it will have. So we will introduce this file system, and then We will look at the schematic editor, and there are few analysis like a transient analysis, the AC analysis, STB analysis. Those kind of analysis will be like the procedure will be explained in this module too. So along with that, we will look at even the Monte Carlo simulation setup, how we can set up that, and how we can run the Monte Carlo simulation on any analog circuit. So these kind of concepts, like basically tool related concepts, we'll study in module 2. So these are the few screenshots. This is the library manager. So these are the set of libraries, and each library has a list of a schematic. Those are called cells, and each cell has a different views. So when you click on the schematic view, you will get a schematic editor. So this is where you draw the schematic. So if you go to launch, and then you can open the ADL. So using ADL, you can run the transient simulation or STB simulation, or you can run even the Monte Carlo simulation like that. So the procedure, the entire, if you want to do any project at college level or in any company, so all the things which are required for you in terms of tool related details, those will be explained in this module.
Will you use only the ZPTK or any other PDK will use?
Yeah, we have a, UMC 65 nanometer technology. Okay, GPDK is also available, and we have one more TSMC technology. Yeah.
Okay.
So
Thank
yeah.
you.
So 45 nanometer and 65 nanometer technologies are available. Yeah. So all the experiments and all the examples we will look at in lab, those will be run, or the circuit will be built with 65 or 45 nanometer MOSFETs. Yeah. So module 3 focuses on a single stage amplifier, the common source, common gate, and common drain amplifier, and we will look at even the source degeneration circuit. Okay, so we'll do the small signal modeling of these amplifiers. So right now, only the NMOS amplifiers are shown here, but we will study even the PMOS amplifier, um, and we will look at the basic parameters like what is input impedance, output impedance, voltage gain, and current gain. So all the concepts will be studied in teaching classes, but in lab class, we will focus on biasing these MOSFETs, because right now it is an open circuit. So question will be how to bias this single stage amplifier. Then we will look at what is the GM and what is the R naught it is offering, and we will try to calculate the output resistance and what is the gain it provides. So those kind of calculations, the parameter we will extract through simulations, and we will substitute those in this equation, and theoretically we will derive all these parameters. And there is a way we can measure the output impedance, and there is a way we can measure even the gain of all these parameters through simulation. So we will do the comparison. So we run the simulation and check how for example, voltage gain varies, and using parameter and using this equation, we will calculate the gain number, and we will try to match those numbers. And a few good number of assignments will also be given on this. Yeah. So module 4 focuses on differential amplifier design. So initially we will study the basic concepts of differential amplification. So what is this single-ended signal, and what is the differential signal, and why differential signals are important. So those kind of basic concepts we will study, and then we will take 5 pack a differential amplifier. So here, first we will write the gain equation, or we will first do the small signal modeling of this 5-pack differential amplifier, and then write the gain equation and equation for the pole zero plots, and what is the output impedance. So what if how to set the sleeve rate of this amplifier, and how to decide the current, the tail current. So those kind of studies we will do in this module. So along with the differential amplifier, we will look at even the current mirrors. So this is the one simple current mirror, it is shown here. So we will look at even the cascade current mirror, and the low voltage cascade current mirror and Wilson current mirror. So all the varieties of current mirrors which are used in op-amp, which are used in band gap. So we will study all the current mirrors. So that it will help in designing the further blocks like a PLL, band gap, op-amp. So these current and it, the basic concepts will also we will study. Like for example, this is a simple current mirror. So what is the output impedance of this simple current mirror? If I do the cascade, if I add one more NMOS, then how the output, the impedance changes, and what are the problem with that? Because adding one more MOS means keeping its saturation needs some VDS, so the output swing will reduce even if the output resistance increases, but there is again the limitation, like output, the swing will reduce. So we will study both positive and negative point of each current mirrors. Okay. So module 5 focuses on feedback techniques. So in the previous module, you studied differential amplifier and single stage amplifier. So to increase the gain, we go for cascading of these differential and single stage amplifier. So to get the higher gain, so that's when to make the gain flat, then we connect it in feedback, the differential amplifier in feedback. So once the connection is done, then then the things will change. The stability is a major concern. So before studying stability, we need to understand few control system concepts. So here in this module, we will look at the general feedback system, the theory behind the general feedback system, and a few basic concepts like error amplifier, what is the loop gain, what is the feedback network. So how to write the transfer function of any a negative feedback system. If it is a positive feedback, then what happens? So those kind of concepts we will study. So along with that, we will look at the Bode plot, we will look at the pole zero plot of a system, and we will look at the root locus and basic concepts of control system. So in the lab, we will try to realize all these concepts like pole zero. So in through simulation basic, you can plot the pole zero, you can get to the location of pole zero. So we will look at the procedure of a simulation setup, how we can get the pole zero plot and how we can get the Bode plot. Those kind of concepts we will study in lab.
So Pankitesh, here you will be also touching on the basics like what plot and how it helps in designing.
Yes.
Okay, so the
Yeah, we
basics
will
will be
discuss.
covered. Okay, okay.
Yeah. Those things will be covered in theory class.
Okay.
And in lab class, we will try to understand those concepts through examples.
What I'm trying to understand, for example, I have good experience on the layout side. Okay. But design side is kind of newer to me and I've been in college long back. So will your theory already cover the concepts which are needed for a person to totally get into design, or we have to
Yes.
read something before? Yeah. Okay.
No, it's everything from scratch. Things will be covered.
Sure. Thanks.
Yeah. So module 6 focuses on the stability analysis. So once you know the negative feedback, how it works, then the next step will be making it stable. In this session, we will look at the frequency response of an amplifier. So this is the one simple amplifier, it is shown here. So, but along with this, we will look at the frequency response of a single stage amplifier, which we studied in the previous module. And also we will look at the differential amplifier, the frequency response. And just to make basics clear, we will look at even the Bode plot of first order low pass filter, and we will look at the Bode plot of a high pass filter, and we will look at what is this a dominant pole approximation and a dominant pole compensation, what it means and why it is needed. Okay, so those kind of concepts will study, because if you look at the op-amp data sheet, you will see that only one pole will be present within UGB. So all the second and third poles will be above UGB. So UGB in the sense when the gain curve crosses 0 dB, so that frequency is a UGB. And if you look at any data sheet of op-amp or amplifier, you will see that second and third poles always appear after the UGB. So before the UGB at lower frequency, you will see only one pole. So that is called a dominant pole approximation. So we will study why it is needed, why only one pole is preferred before UGB. Okay, and what the effect of bypass capacitors here, uh, and the effect of even the Miller capacitor. So we will introduce Miller's theorem and how we can use Miller's theorem for getting this a single pole within UGB. Okay, so those concepts we will study in this module. So module 7 focuses on operational amplifier design and operational transconductance amplifier design. So here we take a 5 transistor OTA and we will write the small signal model, and we will calculate all the parameters which we discussed in earlier module. And along with this 5 pack, we will look at 2 more architectures of op-amp or OTA, that is telescopic cascode OTA and folded cascode OTA. So these two, the advantages and disadvantages we will study, and we will look at all the parameters, like what is the input impedance, output impedance, the gain, the frequency response. So all the things which we have discussed for a differential amplifier and single stage amplifier, so those concepts we will study even for these two amplifiers. Okay, so this telescopic and folded, especially the folded cascode OTA, is very important. So it is used in many op-amp architecture where you want rail to rail input. Rail to rail input means, so here if you look at the circuit, this is the PMOS, right? So this PMOS needs some VT. So if the supply is 5 volt, then the input should be 5 volt lesser than VT of this PMOS. So basically the input cannot go close to 5 volt, correct? But if you have NMOS here, then definitely the input can go to up to 5 volt. But problem with NMOS is it cannot go to 0 volt. Input cannot go to 0 volt because of this VT. So VT is the minimum voltage it has to maintain. But if you combine this NMOS and PMOS together, then you get an architecture where input voltage can go to supply voltage and it can go to even the ground voltage. So those kind of concepts, that is called rail to rail. Okay, so those architecture we will study in this module. So along with that, a few more parameters like how to do the compensation, and what is the sleeve rate, how to set the sleeve rate, how for a particular sleeve rate, so what capacitor I can connect at the output, because finally it is charging and discharging of output capacitor. So depending on the tail current, basically you can decide the output capacitor. So if the current increases, then the charging and discharging of the output capacitor will be faster. So depending on the settling time, you can decide what is the tail current and what should be the output capacitor. So those kind of relation we will study. And power supply rejection. So when the power supply varies, then how much of the ripples or the AC signals that is present in the power supply, that will be reflected on V out. So that is called power supply rejection. So there is a one more called power supply rejection ratio. So this parameter we will study. And for a differential amplifier, the how to improve the PSRR. So that will also we are going to study in this module. So next comes the mismatch and variability. Here, let's say if the current changes, then how the parameters will change. And if because of the mismatch, if the size of these two differential amplifier, differential NMOSes, if its size changes, then how it reflects as an offset at the output volt. So those kind of studies we will do. And in the lab, the Monte Carlo simulation will be introduced. Basically, it does the mismatch analysis, and we will look at the basics of mismatch, because mismatch will have a different, it can be a linear mismatch or it can be a Gaussian mismatch. So which mismatch is appropriate for a MOSFET, we will look at it. And if, let's say, mismatch has for a particular circuit has the required mismatch, how to improve it? By increasing width, whether it will improve, or by increasing the length it will improve, and which MOS sizes should be improved. So those kind of questions will be addressed in this module. So module 8 focuses on a low dropout regulator. So low dropout regulator has different components. So you can see here, this is the flipped voltage follower low dropout regulator. So it is called flipped voltage because we will study why it is called flipped voltage. So if you look at it, is a differential amplifier. So it acts like an error amplifier. So that is connected to one more a single stage amplifier. So this is a second second amplifier, and it is a single stage, and it is connected to the source follower, one more amplifier, and it is connected to a pass gate. Again, it acts like one more common source amplifier. So this PMOS can be this MOS can be either PMOS or NMOS. It can be anything. So depending on application, so in which application with PMOS to use and in which application NMOS to use, those kind of studies, a detailed study we will do in this session. And what is this the resistor network, and how to decide the C out for a given load current, and how to size the pass gate. So those studies we will do. And since you can see here, there are so many stages. It has a differential amplifier, it has 1, 2, 3 single stage amplifiers. So with such a configuration, the DC gain will shoot up, and the second, at this node it will add one pole, at this node again it will add one pole, and here also it will add one more pole. So if you start counting number of poles, it will be many. So here 1, 1, 2, 3, 4, and this can also add one more pole. So total 5 poles are there. So 5 poles means 5 into 90 degree. So the maximum is 5. You can calculate how much it is, 5 into 90 degree. So compensation is a major concept. Okay, so then how to use the Miller theorem for compensating this LDO loop. So the control system concepts we will study, and we will look at how to do the sizing of all the MOSes. So we will look at even the PSRR of this LDO. Okay, and again in LDO there are two set of applications where the capacitor is very large. That such a LDO is called capped LDO. In it will the cap a value will be of the order of microfarad. It can be 1 microfarad or it can be 10 microfarad. Such LDOs are called capped LDOs. And there is one more set of LDO, it is called capless LDO, where the Cout will be of the order of picofarad. It can be 10 picofarad or 50 picofarad, but it will be very small. Such a LDO is called capless LDO. So we will look at the stability analysis of both capped and capless LDO in this module. So module 9 focuses on bandgap reference. So the basic concept we will go through initially. So why the bandgap reference is needed. So if you take any IC, it can be microprocessor or it can be DSP processor or it can be connectivity devices like a Bluetooth or Wi-Fi devices. Take any example, any IC will have this bandgap reference. So we will study why this bandgap reference is needed and what is this PTAT current, what is this CTAT current. So combining these two currents or voltages, how we get a constant voltage which is independent of temperature. So the theories, everything we will study in theory class. So the bandgap circuit, there are many varieties of bandgap circuits, but concepts will remain same. So we will look at 4 to 5 different architectures. So depending on applications, depending on the requirements, the bandgap architecture will change. So we will study in which all applications, which one which architecture is preferred, and we will look at the low voltage bandgap. Okay. So and we will look at the startup circuit. So the bandgap is self-biased circuit. So if you take any self-biased circuit, those circuits will have two operating point. One is zero current operating point. Another one is, depending on the LC values, depending on the sizing, the operating point will change. So the very common operating point is zero current operating point. So to come out of this zero current operating point, we need a startup circuit. So the startup circuit design is not fixed. So depending on the circuit, depending on the architecture of bandgap, the startup circuit can be different. So we will look at 2-3 different startup circuits and its basic concept of implementing the startup circuit. And in lab session, we will take example and we will try to realize all the theories which have learned in theory session in lab session. Okay, and we will look at even the matching, how the current mirror is supposed to be matched. Okay, how this transistor is supposed to be matched, and why it is 1:24. So in matching, how the transistor needs to be placed. So those kind of layout related concepts also we will study. So if you look at these two resistors, these two resistors are same. So whether we need to match these two resistors or whether we need to match this resistor with R2, and the reason for matching these two resistors. So those kind of concepts we will study in this module. But these magic concepts we will study even in case of other previously discussed circuits like LDO, like a differential amplifier. There also we will study the magic concepts. So module 10 focuses on oscillators. So you know that the negative feedback is needed in case of LDO, but in case of oscillator we need a positive feedback. So that is a shift from negative feedback. We are moving to a positive feedback. So here we will look at different oscillators like a ring oscillator and inverter based ring oscillator and a differential ring oscillator. So we will take these 3 examples and we will write a small signal model of this inverter giant, and we will study all the basic the control system related concepts will be studied in the previous module. So we will look at the Barkhausen criteria, and we will look at even the Nyquist criteria. and we will try to plot the Bode plot of this the ring oscillator, and we will start with the characteristics of two pole system, because the one pole system cannot oscillate, and the two pole system also cannot oscillate. But if you look at the three pole system, then it has a option to oscillate. So we will look at single pole system, and we will look at the two pole system, and we will try to study the two pole system, like how we, depending on the zeta, depending on the damping factor, depending on the oscillation frequency, the natural frequency omega n, so how the transient response looks like. And the basic you might have studied in control system classes, right? The damping factor, the entire equation derivation we will study in this module. And we will as I said, we will do the small signal modeling, and we will do the transfer function. We will write the transfer function, and we will calculate the loop gain, because depending on the loop gain, the ring oscillator will oscillate. So the loop gain condition should be met. So that how to meet that loop gain across the PVT. So those kind of analysis we will do in this module. And module 11 focuses on a phase lock loop, like all the control system related concepts we studied for other blocks, we will do same even here. So in PLL, it is little bit complicated. For that, we first write the mathematical model of voltage controlled oscillator and phase detector, and there will be a lot many blocks like a low pass filter, and we will combine all these three blocks, and we'll try to write the equation and relate it with the second order equation what we studied in the previous module. And we will like we will check if zeta varies, then how the frequency will vary, how the phase will vary, and how the step response to this PLL will vary. So that kind of analysis we will do. And in PLL, few more problems will be there, like a phase alignment. So those kind of problems also we will discuss in this class. And the PLL dynamics, the type 1 PLL, type 2 PLL, and the PLL design procedure we will do in theory class, and in lab class we take example and we will try to follow the procedure. So PLL also needs a charge pump. So charge pump is like a hot domain right now. So many companies expect expertise in charge pump. So charge pump, or you can hear the switched networks, switched cap network. Okay, so charge pump you are used in various applications. It can be used as a voltage regulators as well. So we will take 2-3 examples, and there will be good amount of assignment will be given on this charge pump. So PLL needs a charge pump also. So we will study even the basics of charge pump in this module. So module 12 focuses on data converters. Like there are varieties of data converters, like a flash ADC, some are parallel ADCs, dual slope ADC. There is one more called sigma delta ADC, and successive approximation ADC. So we will look at the basic few architectures, and we will take few examples, and we will try to relate for ADC, few set of parameters will remain same, like a signal to noise ratio, total harmonic distortion, and E knob. So these parameters we will study one by one, and we will take one architecture from successive approximation ADC and one from sigma delta ADC, and we will try to realize those parameters in this ADCs. And we will look at the sample and hold circuit, because every EDC needs a sample and hold where it samples the input signal and it holds on a capacitor, or there's a different devices to hold the voltage, and then it does the analog to digital conversion. So the sample and hold, the settling requirement, those kind of parameters we will study in this module. So the module 14, like the course contents are completed by module 13. Module 13 is the last module which has technical details. So module 14, in this, there will be mock interviews and personality development classes are conducted. And along with that, few points will be on like a resume building and mock interview, yes, and personality, yes. And once all the theory and lab sessions are completed, then we will have a test. Okay, once whoever passes the test, then those people will be given with a placement support. Yeah, so this is all. So if anyone has any questions, then they can ask. So a few points from my side is it's not just a theory class. Even layout related basics will be taught. As a designer, like uh, the designer should know the layout aspects also, like a matching. Is it a common centroid matching is needed? uh, is it a interleaving is needed? What is during etching, how the mismatch will come? There will be linear gradient in variation, and second order gradient will also be there. So that kind of layout related concept will also be taught in this course. So that is taught because the analog circuit designer is supposed to know it. The sizing of the MOSFET has to be done to support the layout. That is possible when you know the layout concepts, few layout concepts. So even for each circuit, how the layout needs to be done. As a designer, we need to tell the layout guy how it has to be done, which matching needs to be followed, and how the uh, what is this guarding means, for cancelling the noise, what all things can be done in layout. Those kind of concepts will also be covered in this course. Yeah. So if anyone has any questions, then they can ask. So this is the right time for them.
Venkatesh, I just wanted to understand how will be the classes and theory? You'll be sharing material with us, and how do the lab get conducted?
Yeah, the soft copy of uh, the concepts or the PPT will be will be given to each student.
Okay.
That's how you will get the material. So you don't have to buy textbook or anything like that. But if you need more detail, then definitely we will recommend which all books to buy. And
Okay.
this is related to theory. Regarding lab, using VPN network, you will be given with one VPN session. So there you
Okay.
can open the cadence, and it will be specific to you only.
Okay.
Each students will be given a separate VPN sessions. So
Okay.
in that way, you can easily log in, and you can open the cadence virtuoso tool. There you can create a schematic and you can run the simulation.
Okay. Okay. Sure.
And
And
those schematics will be saved, and you can access those schematic even later.
if suppose while doing the lab, we need some help. So will the access to teacher, you will be teaching us, right? So
Yes,
will the access
definitely.
to you will be there?
Yeah,
Like,
yes, definitely. See, see, we have a specific lab session. So in that
Okay.
lab session, we can include discussing even the questions or queries, and
Okay.
there will be assignments will be given. Lab
Mhm.
assignment will also be given. So those
Okay.
solutions we will discuss in lab session.
Okay. Okay. Thanks.
Any more questions? Yeah, one question is, in which company am I working in? I'm working in Texas Instruments. So I have 12 years of experience and I'm working in Texas Instruments. Okay. Yes, so we can cover. Question is, can we cover some other design like iOS and GPIOS? So it depends on the bandwidth of, like we have a time 16 weeks. So within that time, we are targeting some syllabus. So if we are able to complete it, and if we are able to go fast, and if we have a time, then definitely we can focus on iOS and GPIOS. Uh, so the one more point is, the project will also be there, a small project. So it's up to the interest of student, because designing PLL itself is a big task. It's not going to happen in 2 months or 1 month. It's going to take significant time and effort from your side. And if you take even ADC, and even there are so many IPs, LDO, we need to discuss, ADC and PLL. So designing each block itself is takes lot of effort. So in that way, so by the time you reach project, you should know where you want to get expertise. So based on that, you can choose the project. Okay. Okay. The further details, I think Buona will explain you. If you wanted to opt for this course, then you can contact Buona. Yes, Buona, I think we can close this demo session. Okay. Okay. Thank you. Thank you all. Okay. Thank you.